Power and sample size estimation, the 5 things that you need to know. What are the essential questions? Well, you need to be able to define the null and alternative hypotheses. You need to be able to define type 1 and type 2 error. What is power? What is needed to estimate sample size? And what increases or decreases power? So let's start off with an example about the truth. This is our goal. We can start understanding power and sample size and type 1 and type 2 errors if we look at the justice system, a legal scenario of a jury trial where someone is innocent or guilty, but we don't really know the truth. There's a decision made of guilt or innocence, and if they really are innocent and they're found to be innocent, then no errors have been made. And if they really are guilty and they're found to be guilty, then again, no errors have been made. But there are 2 ways to make a mistake. An innocent person, a truly innocent person, could be found guilty. That's a horrible error. That is convicting the innocent. That's what we call a type 1 error in statistical testing. The other kind of error that can be made is that a guilty person goes free. They are found innocent. This is similar to what a type 2 error is in statistical testing. If you look on the right side, again, our truth, we never really know. We'll never really sample an entire population to really find out what the true estimates are. Either our treatment intervention groups are the same or they are different. What we do is observe data and make a choice between our null and alternative hypotheses. And they are either we find the groups to be the same, that is, we stay with the null hypothesis, or we find the groups to be different. We go with the alternative hypothesis. So if the groups are really the same and we find them different, we're choosing a new treatment and saying that this new treatment or this new intervention is better, but it's really not. That's the type 1 error. We have found for the alternative hypothesis when the null hypothesis was really true. The second type of error, called a type 2 error, is when the groups are really different, but we've concluded that they are the same. So we're missing a new, better treatment or a new, better intervention. Again, this is an error. This is called a type 2 error. So we have found for the null hypothesis when the alternative is really true. So there really is a difference, but we haven't declared there to be a difference. So those are the 2 types of errors that we have to deal with in our statistical testing, specifically when we apply it to clinical trials. So the first step, obviously, is to define your hypotheses. Since we'll be choosing between our null and alternative hypotheses, they need to be very specifically defined. The null hypothesis needs to be clinically or scientifically meaningful, and the alternative is mutually exclusive of the null hypothesis. This is also called your research question. It's what you hope to show. So from there are 5 things that we need to understand to determine our sample size. The first one, based on our hypotheses, is what is a meaningful difference, and then also what is the variability about that difference. When we say meaningful difference, that means once you've selected your endpoint, you can determine what difference between your groups is meaningful for that population. Not just what difference will get you a significant p-value. It needs to be clinically or biologically significant. So if you're dealing with human participants, say of age 40 to 60, and you're looking at a new weight loss intervention, powering a study to say that intervention B is better than intervention A because the group B lost 1 more pound than group A is not clinically or biologically significant. You would need to determine if this is a standard or normal BMI population, then maybe it's 5 or 10 pounds to be clinically or biologically significant. If you're dealing with a population that's on the lower end of the BMI spectrum, it might be a smaller amount of weight, whereas if you're dealing with a group on the upper end of the BMI spectrum, it might be a significantly large amount of weight, say 20 or 30 pounds difference, before you would say that those interventions were significantly different. For continuous variables, you will need a mean and a standard deviation. If you go through statistical theory classes, you learn that means and standard deviations are independent of one another. So you can have a group of people that have the same mean but different standard deviations, or you can have a group of people that have the same standard deviation and different means. So for continuous variables, you need both a mean and standard deviation estimate. For categorical variables, you need the event proportions, because when you're looking at variability, if you have a categorical endpoint, then the proportions are defined and you know the standard deviation. So defining a proportion defines the standard deviation for categorical endpoints. For continuous endpoints, you need to have an idea of the mean difference and then the standard deviation, or the variance of the change, or the variance of the difference. Prior studies or pilot studies can help you with all of these estimates, and you always want to overestimate your variability when you can. Going back to our first type of error, or a type 1 error, this is what we know as alpha. This is how we make a decision between our null and alternative hypotheses. In standard statistical testing, it's often 0.05. You will see it be 0.01 or even 0.001 if you have a very large sample size. But sometimes you'll also see alpha set at 0.10 for pilot studies or maybe for interactions. The type 1 error is related to our p-value, or how we make a decision between our null and alternative hypothesis. So remember, our p-value is how we make a decision. It's how we choose between the null and alternative. Our p-value is how likely it would be, given that the null hypothesis is true, to see the results we saw or those more extreme. So the p-value, what we're looking for, is small. Remember, we want to know or have an idea that what we've seen was not likely to be seen, that it was an extreme result, and therefore we would be more likely to go with the alternative hypothesis. If what we observed is a very common or expected result, then we would tend to stay with the null hypothesis. That would give us a large p-value, and we'd stick with the null. Remember, our type 1 error in the legal scenario is when someone is truly innocent and we found them guilty. In the statistical scenario, it's when you conclude the alternative, or you find for the alternative, when the null is really true. So you've concluded there is a difference between your treatment or intervention arms when there really is not a difference. Again, this is like finding someone guilty in a trial when that person is really innocent. Understandably, we want to minimize the likelihood of a type 1 error. That's why it's often a very small value, 0.1 or smaller. So we need to know our meaningful difference and our standard deviation, or our variability. We need to know the type 1 error. We also need to know what our power is. Power is determined by our type 2 error. But we are not as concerned with minimizing the type 2 error. Think about the legal scenario. We're really concerned about sending an innocent person to jail. We are also concerned about letting a guilty person walk free, but not as concerned as we would be by sending innocent people to jail. It's usually 20%. Sometimes when you have a very large sample size, you will set your type 2 error at 0.10, or if you're doing a confirmatory trial, you'll set your type 1 error at 0.10. Because we're very concerned about choosing the null when the alternative is really true. We want to minimize that likelihood. Sometimes in a pilot study, you will see a type 2 error set at 30%. We're not as concerned with making that error. So how are power and error related? You often hear people talking about the power of a study. You very rarely hear them talking about the type 2 error of a study. So remember, type 1 is the likelihood of picking the alternative when the null is true. So you've made the wrong choice here. That's a type 1 error. You've sent an innocent person to jail. Type 2 is the likelihood of picking the null when the alternative is really true. So we've made the error in the other direction. We should have declared a difference. We didn't. We should have sent someone to jail. We didn't. Again, you've made the wrong decision. That's our type 2 error. What about ensuring we make the right choice? Choosing the alternative when the alternative is really true. So there truly is a difference between our interventions, and we want to increase the likelihood that we declare there to be a difference. That is the power of your study. Power is 1 minus beta, or 1 minus your type 2 error. So remember, our type 2 errors were pretty commonly 0.20, sometimes 0.10, and sometimes 0.30. That would make our power usually 80%. So we want to be 80% sure that if there really is a difference, we'll declare there to be a difference. In pilot studies or in small sample sizes, sometimes we'll say that our power is only 70%. And sometimes in very large studies or in confirmatory trials, we power things for 90%, because if we expect to have a lot of dropout, we still want to have 80% power when the study concludes. So to have 90% power, we would need more people, right? That makes sense, because to be more sure or increase the likelihood that you'd pick the alternative when the alternative is really true, you want higher power. That needs more people. But some of those people will drop out. So by the time the study ends, you want to ensure that you have an 80% likelihood. So I need a meaningful difference. I need a standard deviation. I need an alpha level. I need my power estimate. All of those things will go towards my sample size, or n. All of these things can help you estimate the sample size. If you know your sample size, or if it's restricted, so if you're doing a study from an already existing population, then your n is fixed. So if you already have a sample that you're using, then your n is fixed, and you can figure out either the difference that you can see, you can estimate the variance. Knowing any 4 of those things helps with the 5th one. Oftentimes in clinical trials, unfortunately, we have budgetary restrictions, and so you need to have an idea of what sample size you can literally afford, dollar or monetary wise. So you understand how much it's going to cost to collect each endpoint and to follow each person for your prescribed time. That will give you an idea, once you subtract off administrative costs, how much sample size you can afford. And your statistician can work from that point backwards to talk about meaningful differences. It is all a give and a take, and all 5 of these things are related. So how are they related? If you make your alpha larger, you will increase power. That is, if I make it easier to reject the null hypothesis, I have a larger alpha, so an alpha of 0.1. That means I have more space to have a p-value less than alpha. That means I'm more likely to reject the null. It makes it easier to pick the alternative. If the alternative is really true, then I've increased my power. If you increase the difference you're willing to detect, you will also increase power. It's easier to tell the groups apart if you are willing to accept a larger difference. It is much easier to say 10 pounds of weight loss is different between 2 groups than 1 pound of weight loss. So the larger the difference, the easier it is for me to end up in the alternative. If the alternative is true, that increases my power. Now be very careful on both of these first 2 points, alpha and the difference. Making them larger increases your power, but it also increases your type 1 error. Remember, it means that you can reject the null when the null is really true a little bit easier. So it's a balance. If you make your standard deviation estimate smaller, you'll increase your power. But that's only on paper. If you decrease the standard deviation, it's easier to tell the groups apart. You have tighter estimates, so it will be easier to end up in the alternative. If the alternative is really true, then you have higher power. But remember, these are only estimates. So alpha, power, and the difference that you're willing to accept are relatively fixed levels. What you estimate your standard deviation to be, you could be totally wrong. So don't just lower the standard deviations in your estimates to show that you have higher power if you really don't expect that standard deviation. Also, performing a one-sided test versus a two-sided test will increase your power. You're only looking for one difference. I'm no longer looking for something to be greater than and less than. I'm only looking on one side. So I can put all of my eggs in that basket, so to speak. If I do a one-sided test, holding everything else the same, versus a two-sided test, I have more power to find a difference. More power means it's easier to pick HA. If HA is true, I have increased my power by making it easier to pick the null. So what do you do? When planning, there are some things to avoid and some things that you can prepare for in advance. Don't skip this section in your grant. Even if you are using a pre-specified sample size, reviewers still need to see that you have thought about what you might find in your research. They do not want to award money to guarantee you to find for the null hypothesis. Remember, it's also unethical to underpower a study. That means that you've exposed people to risk with no chance of finding for the alternative. Do not skip this section. Don't guess blindly. Don't rely on power and sample size from other studies. So don't look at another study and say, well, they only needed 150 people. That means we only need 150 people. What if some of their estimates were wrong? What if your estimates are different from their estimates? So you need a power and sample size estimate tailored to your specific trial. You can certainly rely on prior studies to get estimates for differences in standard deviations. You can rely on prior studies to look at dropout rates. You can rely on prior studies to look at how many people you'll need if their estimates hold true, but don't simply cut and paste a prior power and sample size from another paper. Also, don't assume you'll recruit everyone in your clinic. Less than 2% of people participate in clinical trials in their lifetime. You can assume that is the same for your specific clinic. You won't necessarily get everybody, so if you see 100 patients a year, you won't get all 100 of them to participate in your trial. So have realistic estimates about the proportion of people that will meet the inclusion-exclusion, the proportion of people that will enroll, and then the proportion of people that will complete. That leads me to say don't assume 100% trial completion. There will be dropout. No matter how short the trial duration, it is unlikely you will have 100% data completion. That leads you to the things that you need to do. So you can use information from pilot or prior studies to hone in on the estimates that would be useful for your power and sample size. Know your endpoint. What is a meaningful difference for your population at hand? Determine your desired power and your desired significance level. Use a variety of standard deviation estimates. Always overestimate. It is the single largest killer of a study. If you estimate a standard deviation of 1 and you see a standard deviation of 2, you will be underpowered. Consider dropout, so protect with a higher sample size if possible. Again, that's why you'll see trials powered at 90%, so that when they lose participants, when they lose people, you don't have to fall below 80%. If you are the one making the sample size estimates, use a table or a graph. Graphs can be very helpful with several lines to show where the power falls out for given estimates. Take all calculations with a few grains of salt. You will be wrong. The question is by how much? Fudge factor is important, and again, the best fudge factor is overestimating your standard deviation. Round up, never down. If you estimate 10.01 people per arm, that's 11 people. So instead of 20 people, you would need 22 people. And remember, if you have dropout, you could be down under 20 people very quickly, and then you're immediately underpowered. So always round up. And remember, analysis follows design. Your statistician will help you based on the design that you've picked. That will predict the analysis that you will use. That analysis will determine the sample size calculation equation that is needed. But of course, all of this is done using computers. You just need to be willing to have the discussion with your researchers and your statistician about your hypotheses, your endpoint, the desired power, the significance level, a meaningful difference, standard deviation estimates, and what sample size you can reasonably afford.